in the spirit of all the discussions that we have had yesterday, I've tried to minimize the amount of math I'm using in this lecture slides. But again, I have another part of slides which, if you want to, we can go back to the fundamental math behind that. So this will be a bit more repetition of what Satyendra was speaking in the morning on the transformer part. I'll give you some overall motivation, how the things work internally, and what could be the broader use cases. And after that, I'll go on towards usage of such networks in face recognition, and that could be more or less generalized to other domains. And then we start looking towards the detection of such content. So far we have been focusing only on creating the content. Now we also need to look at how to detect that content, right? Good. And then in the spirit of also full disclosure, I should also acknowledge that there are some slides, some figures taken from other lectures, other popular lecture series. So wherever I've taken some pictures, I just put the link and reference to them, so you could go back and trace them. All right. So what is transformer? Again, it's nothing but a fancy name for feed-forward network based on attention, right? So far we have been learning everything about feed-forward networks. We learned about how to propagate the gradients, back propagation, forward propagation, and so on. It exactly follows the same logic. And the two key things that you need to know here is this paper, that is the a paper that was written in 2017 by Waswani et al. And then they introduced these two different modes of attention, which is shown on the right side. I'll come back to the attention part in a moment. But then this is the base paper that you want to start with if you want to start learning on transformers. Okay, this is again a slide I took from another lecture, and then I was trying to look at what exactly happened so that we came at transformers right now. So we started with word embedding somewhere around 1990s, and then there has been a lot of developments inside the neural language models, and then there has been a number of models that came out for multitask learning, which is one network doing multiple things, right? And then we have in 2015 the attention was introduced, and then making use of attention, transformers were introduced in 2017. And then again, as with any other research work, you always have some scope for improvement, and the improvement came extensively in 2018 when they introduced the contextual word embeddings and pre-training modules out there. And as we all know, 2019 was the time when GPT came out, the first version, very crude version of what we have right now, but then it has been improved ever since, right? So here is the timeline from static to static word embeddings all the way to the prompting. And I was also looking at this textbook written by one of the co-authors. Sorry, I forgot to mention the source there. I can share it with you later on. So if you look into this tree here, you can clearly see that the transitions has increased from every single place. Let me try to see if I can zoom in. And here is where we are talking about the popular models such as Glow and then Word2Vec and so on, these kind of models. These are very well-known models for extracting the embeddings from the text, right? So we start from this, and today we see a lot of different branches. As we can go up here, there are some of them which are open source, some of them very closed source. For instance, Llama is a closed source, while GPT is open source, Cloud is open source, and so on. And to come from this place, Glow, to all the way to this particular place up here, there has been a number of improvements that has done over the period of time, right? Every single time there has been something new that has been integrated, and then there has come a lot of specialized models. And even here, if you look at this, we are just referring to as Chat GPT, but here you can see another branch which is specializing on software engineering. So for those of you who do not want to sit and code, you can use such engines, and then you can prompt properly, and then you get the code completely. And if you're not tried it out, you could also try it out even on ChatGPT or even on models like Cloud. They actually give pretty good code. I mean, again, the caution is here: do not take the code as it is from them. Sometimes they tend to make a lot of mistakes, some obvious mistakes. Just scrutinize it, and then you can use it. All right, and then again, as you can see, this is the model 4 that is updated by, I think right now we have 4.0, the mini version of the GPT-4. So there has been extensive developments in this field. Okay, then if you had already the static embeddings back in the days, why should we really worry about the context, right? So in the morning, we were talking about a particular example where the context was mentioned, and now I'm taking the similar example here. And in this case, you can read the sentence which says that the animal did not cross the street because it was too tired, right? So, well, it's the famous saying from this: "Why did the chicken cross the street?" And they have tried to explain it in many different examples. I took one of the example there, and here, if I have to complete the sentence, and if I stop at a particular point called because, and what would be the next word? So that is the context here, right? It can refer to, in that particular sentence alone, if I see, there are two possibilities. One, the street can be it. The other one is the animal can be it, right? There are only two possibilities. Now, this is in the terms of completing the sentence. Now, it could also be looked up on the other aspect. What if I have a missing it? So if that particular word itself is missing, can I plug that in back? Right? So that is the whole idea. So now in this case, what is happening is that the static embeddings, they do not necessarily capture this kind of transitions. And this can be generalized to some extent to a lot of models like BERT, Roberta. There is this the GLOW, the Word2Vec, all this family of extraction feature, the feature extraction methods. They only extract the embeddings from whatever you give them, right? So they don't fill in any context. So how do we solve this one? So now we are going from this particular problem towards solving the problem. So one of the problem, the solution is you have an input, there is a transformer in between, and then there is an output. So and this could be multi-purpose, right? For instance, it could be filling the sentence, completing the sentence, as well as it could be a case where we are trying to translate something. So in this case, there is an example where we are translating something in French to something in English, right? Or the vice versa. Now, if I assume that as a magic black box, so what does this black box consist of? It only consists of two different parts. One is an encoder, which converts the French language into something that is in the latent space. And once I understand the latent space, maybe there is a mechanism where I can map that into another space and then put the words back. So then comes the decoder, right? So now if you assume it in all the contexts that we are talking about, it's almost similar to, let's say, in encoder architecture, encoder-decoder architecture, which we saw in variational autoencoders. The only thing that we are not worrying here is about how we are mapping those things into the other part, right? So that is something that we will discuss later on. Now, if you go a bit deeper into this one, there is no reason that why I should have only one encoder. I could have n number of encoders, right? So just like in deep convolution layers, I can have n number of layers. Exactly the same way, I can have n number of encoders. The only thing here we should worry about is that the more number of encoders we have, the equal number of decoders should be there. So there should be a one-to-one correspondence, right? And then let's break the encoder even further down and try to see what is exactly in the encoder. Within the encoder, as I told you, there is only one concept. This is the feed forward. And I told you it's a fancy word. Transformer is a fancy word for feed forward plus attention. Then comes the attention block. So forget about the attention block for now, how it is done. I'll explain you how it is actually done. But then if you invert the whole process on the other side, what you're going to get is that you have a self-attention network and then attention network for encoder decoder, and then you have a feed forward again. So you have the text that is going in and the text coming out. Now in this case, I'm just taking the example of text, but you could also take it as an image, you could also take it as an audio signal, you could also take it as any kind of other signal that you would be interested in, right? Okay, now let's try to understand what is the contextual meaning, right? So a word can mean different thing in different contexts. We saw the example of it. It could be something else. It could be some other word which could have two different meaning depending on the context. So we want to catch that encoding. We want to catch the context of that word. So the whole idea here in the transformers is that we want to get that contextual embeddings, not pure embeddings. So that's the only difference, right? And then the idea here is that if you have to catch the context, we should also catch the words before and after that. So most likely the words before that, but it could also be words after that, right? So if you are trying to fill in the sentence, then you are capturing both the context. But if you are trying to fill only the next coming word, then you are looking at all the images that are in the background, okay? And now you could also think of similar situation in video, right? So if you are looking at a particular car driving on a road, you could already estimate what could be the next scene that you're going to approach. Right? So assume that you're driving in a straight road, so it's most likely that there is one building, then comes the second building, right? Unless you encounter a completely different situation like a roundabout, it should be more or less approximatable. Now, how do we do this? Now we established the reason for finding the contextual embedding. I think when you come, it stops. And then we have the part. What is remaining is like, how do we compute the attention? So if we figure this one out, then it's all about putting the things together, right? Multiple things together and then building our own network. So let's see, let's look at something at a very high level. So let's assume that we have 4 vectors, x1, x2, x3, x4. It could be anything. Now these vectors are nothing but the vectors that is coming from my encoder network, like BERT or Roberta or Word2Vec and so on. And then each of them can be assigned for 3 different roles. So anytime we talk about attention, we talk about 3 things. We talk about query, we talk about key, and we talk about value. The current element that is being compared to the preceding inputs is nothing but the query, right? In our case, what was that? It was, we were looking at the word it. So if we are looking at this one, then we are looking at the word before that, right? So this is nothing but the query. And then the second thing is all the things that is being compared to, so those becomes the keys, right? So you have a key, and so on. And particular corresponding to this each key, then you would also have the values. Is there anybody that is coming from object-oriented programming background? Java? You all use Java, right? So you know that in the hash maps we have this key and values, which is a very similar concept here, right? So for every single thing that we are encoding, there is a particular unique value that is associated with it. Even in Python, right? Tuples, in the dictionaries, yeah. So this exactly is the concept which we are encaching here. The only thing is that then comes the query part. So how do we combine all these 3 things to create self-attention? Now, if you look at that in a manner where it is pictorially depicted, here you see that anything that is coming from x1 passes through an attention mechanism, and then you are getting a a1. So that is your output, right? Attention 1. And the same thing for x2, you would typically get a2, but now remember for a2, you also need an input from x1. So that's where the arrow is going from x1 towards the attention mechanism, in addition to the input from x2 itself. And then you can now build upon this one, right? So if I'm taking x1 from here to this one, then I could also take this one from next one to the next one and to the next one and so on. Right? So what are you trying to do? You are trying to capture the context of the whole sentence. You could also say that, well, I don't want to capture the whole sentence. I only want to capture three words before, 1, 2, 3. But then your model is going to be very weak, right? So the more context you capture, the more informative the model becomes. Now, in that case, if you just also take a different look at that one, right? So as I told you, like it in this particular sentence will mean 2 things. One, the animal. The second one is the road or the street that we are talking about, right? Only 2 possibilities. There is nothing other than that. So what do? I try to find the similarity between the words in co-occurrence, right? I try to see how often does it come with every single word that is coming there. As simple as that, nothing more fancier, right? So if I have, if I try to read all the literature available in the world, I will see that the and it never comes together. The chances of them, right? And animal and it, maybe they come together. And then didn't and it, they don't come together. Cross and it don't come together. Okay, very occasionally it might come as I'm going to cross it, but it's very rare occurrence, right? And then you have the and it, road and it, because it. So if I'm going to make a simple notation out of that, just taking a toy example, if I read 100 books, in 100 books, D and it combination doesn't come anytime in all the 100 books. Okay? So now let's assume the animal. Animal plus it. Maybe I have read at least 50 times in 100 books, going by the rough probability estimation. So 50 out of 100. And then next one is it plus it. So let's assume that is almost, let's give a small probability, right? Let's say 5 out of 100. Yeah? And then the next one is cross. That would be maybe 3 out of 100. And then in the other context, it would be D. Again, it's 0 out of 100. And then the next one is road. Again, this would be around 40 out of 100. And then because is again maybe 0 out of 100. The co-occurrences, right? Now, by simply doing this toy example, now we can already see that the probability of these two coming together is very high, right? So I can say that this has the highest score, which is nothing but 0.5, and this is 0.05, and this is 0.030, 0.4, 0.0, and then 0. Now, in some way, I have established this similarity metric, right? I'm not told how I've done that. I'll come back to that later point. But at least now we can see that, okay, when this word is coming, most likely a word that should come there would be this one, right? So you're trying to estimate that, the probability. And then comes you can continue further, right? Let's assume that if you make a simple continuation of that one, then we, after the it is completed, then we're going to complete it with next part of the sentence. Again, then comes this two words, right? Because it was too tired, it was too wide. Now the context again changes. In the first sentence, we're talking about the animal. In the second one, we're talking about the road itself. So what is that we are targeting? Are we targeting the animal itself or the road itself? So if our context is to model the road, then we would prefer wide by looking at something like this, by looking at the tables. If we are trying to look at the animal, then we are going to look at the first word, right? So this is the idea of combining and building the context for any completion task we have. And then so the way of computing the attention for any particular word is nothing but it's a simple definition which is saying that you compute the embedding for a particular token and then attend to that and then look at the previous tokens and then see what is going to be coming to the next section, right? And this is a very simple trivial example that I took. Now let's make it to the real example there we had. So we had 8 tokens, right? So we had how many? We had the animal did not want to cross the street. So there are like 8 different words. Okay. So now what is my goal? My goal is to predict somehow this x I. So this is the word in the question, right? And if that is the word in the question, so what I could do is I could first find the weighted sum of everything by looking at the score between them. Now here I took a simple illustration that the score was like this. But in theory, what you're going to do is you're going to do a dot product, right? So how many times it is being occurring all the times together? The combination of I and J. I and J. 1 and I, 2 and I, 3 and I, and so on. Every combination we are establishing a matrix which is something similar to like this. And then once you have that score, we're just pushing it to a softmax layer because we're going to use a network. And then we're getting a score. And if the score is less than a particular threshold, we say that, okay, that is not interesting. If it is greater than a threshold, then we take that. So in this case, again going back to the same example, so here the candidate would be this one and this one. Right? So we have identified 2 potential candidates. And now again you can make it more better by adding all the individual summations for all the single words. And then when you do that, you see that the probability is highest for this one rather than this. Here's an idea. Okay. So now we are doing a very simple trivial task, and in this case, I'm taking only one attention layer. Okay. So what does this mean in practice? So there is a very nice demo I will show you in a short while. So here they are taking a 5-layer encoder and then trying to see input to input, and then you can see that every single time the word is coming up there, then there is a mapping to the next word, which is potential heat, right? So you can see all of them pointing to that based on this simple calculation. Everybody with me? Somebody still confused? At least you got the main motivation and intuition, right? Okay, good. So now let's dig a bit deeper into this one. So what exactly happens in the whole process? So every time I have a particular word, let's say I'm taking the example of word thinking. It's a nice illustration in that particular website. I just stole it. From there, you can see that you have x1, which is nothing but a vector, right? Anything that you pass through a network, you get a fixed length of vector. Whether it's Bert, Roberta, or word to vec, glow, anything that you send. This embedding is shown in the green part in the top, and then you can also see that the word on the right side also has the equal length. Gives an idea? So it's nothing but any network, any of your favorite network, you pass the word or the image, then you get a fixed length vector. And then you have the queries, Q1, and then you have keys, K1, and then you have the values V1. Now, where does this key and value come from? Q and K come from, Q, K, and V. Any ideas on where it's appearing from? Probably from the embedding. From the embeddings? From the embeddings? But how are those embeddings extracted? They should come from somewhere, right? I'm passing the input thinking into a network, and I'm getting the embeddings.
They are multiplied by weight matrices of query key and value.
Yes, they're multiplied, but where are they coming from? They should be coming from somewhere.
The same embedding, like embedding of thinking.
From the embedding itself?
Yes.
If I'm taking the embedding itself and processing it, what is the new added value to that?
Sorry?
What is the added value if I'm using the same embeddings to get Q, K, and V?
So initially we generate QKV and QK and V for both the embeddings.
Yeah.
And then we come for the computing the attention. Then if we are computing the attention for thinking, then we will do it for thing itself and then with machines. And similarly with machines also.
Sure. Yes, that's very correct, right? So what I'm asking you is that this one, and this one, are they independent of the x1 or are they dependent on x1? Do they have a direct relationship?
Dependent because they are being multiplied. X1 is being multiplied by the query matrix, the key matrix, and the value matrix.
Right.
So it's being derived from there only.
It's derived from the same word, that I agree.
When we are saying that there is a lot of embeddings which are created from some data set, so those are embedding parts.
That is the first part.
Yeah. So when I'm asking some query, that should go in the query part.
No, that is not.
So
if I'm asking this sentence, what should be the next one?
Yeah. So that is the final formation part, right? So what I'm trying to say here is that we have this. Let's say we have the embedding. This is the embedding that is of vector length 4, x1, and this is coming straight away from the word, right? And this word should also have a different meaning, and that would give me q1, right? Now if you see the length, something happened. Okay, if you see the length of q1, right? k1 and v1, they're all different lengths. You see that one there? It's graphically represented, but that is one, right? So then you have q1, then you have k1, then you have v1. So the way we are deriving this is by training some dedicated networks which can map them into this kind of q1, v1, and k1. Okay, so those are again a set of auxiliary networks which are trained as an encoder.
So they are taking values from the x1.
Yes.
But not the whole set.
Not the whole set, no.
Parts of that.
Just parts of that, right? So we have the query, that is the token that we are interested in, that we are focused on, and then key is nothing but the tokens that we are comparing against, like all these potential words that are coming out, and then value is nothing but the information that we are retrieving based on the attention. Now, if you have these three auxiliary networks, what is that we are ending up with? Now we took one simple example. Now you keep on appending multiple keys and queries and values. So what happens is it turns out into a matrix multiplication.
So it's a semantic recursion.
It's a semantic correlation, right? Yeah. So you are trying to keep the old relationship here. So you have X matrix, and then you get a new matrix which is WQ, which gives you Q. This is nothing but the matrix multiplication, right? Column wise versus row wise. Okay, let's see. Let's try one more time. And then you have the similar thing for query, and then key, and then value. For every of these things, you get three different matrices.
So it means that for same query we are using three different weight matrices
Yes.
to create some value.
Exactly. So for every single word, you have three different weight matrices. These matrices have to be derived from beforehand, right? So which is nothing but a training procedure again, right? So once you have that one, now you can say, since those are all giving you different information, I can use it to create the attention mechanism. And pictorially, if you look at that one, right? So what is happening? You have this WQ, which is here in the top part, and then you have K transpose, which is from here, that is coming here, and then you have the V part, which is being multiplied here to get the together with the soft matrix. And there is a magical term here. The magical term is this D of K, right? This D of K is nothing but the square root of your total length of embedding size. So if the embedding size is 84, you will divide it by 8. If it is 512, you will divide it by the approximate square root of that. Okay? So depending on whatever you are deciding, you will get that one. But in terms of mathematical representation, you can now see that it's a simple matrix multiplication, all of them. So if I have all the three matrix multiplication, and then to compute the similarity of the current element with xi with some prior element, all I need to do is that we need to do some dot products, right? So which is what we were doing, and then we summed it up, and then we took the what is it called? Then we divide it by the total number length of embedding. Now, make it a bit more sophisticated. This exactly is what I showed you in the matrix multiplication. You have the QI, you have QJ, and then you have the total number of embeddings. Now, the interesting part here that you should remember is that the interaction is always between two occurrences, xi, xj. In this case, it is QI, QJ, and then this is remaining constant. If you relate this back to the previous example that we took, what did we say? We said that we were going to take a dot product between two elements, x1, x2, and then we try to see the maximum probability of everything. But that is a very crude way of looking at it, because there is more semantically rich information that we can capture in this context, in this formula, than the very crude formula that we are doing the dot products.
Okay, so basically it's trying to get a meaning from the noise on the basis of recursion. If there is a recursion, then there is a meaning from the noise there.
What do you mean by recursion?
Recursion means the emergence of one pattern over and over and over.
Yes. So the similarity of how do you say the occurrence patterns, right? The occurrence patterns. Yes. Okay. So now all we did was that we went from very simple formula to establish this formula, which says that the attention for a particular value I and j is nothing but the score, the maximum score of xi and xj given a particular question. Okay. Good. So now if you're trying to implement this one, what happens in this case? Now this is again the same model that we were looking at. So now you see everything is pointing to 1. In a short while, I'll show you something even more interesting. At this point of time, I was just using one attention, right? Who's stopping me from using multiple attention? Now, if I know that there is a model for computing such kind of occurrences for French, there is a model which is known for computing German words, and then for some other words, I can have multiple attention models, right? So whenever I'm typing the prompt, I could mix and match. I could write part of the sentence in English and part in French, and each of them can be decoded very easily in this case. So that's the practical implication, right? So very often, I'm very sure that many of you, when you're writing your text messages, you are mixing Hindi and English, you're mixing your local language and English and so on. So in such cases, I can have dedicated models for each of them, right? So now I'm having a stacked matrix, which is W0, 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 QKV, and then I introduce W1, 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 and so on. I can keep on introducing multiple things. So as long as I have that one, then my prediction ability becomes much more stronger. So in that case, in the previous case, I had this unimodal distribution, right? So this is also another example that I took from that particular website. You can refer to that one later. So here you see that when you have unimodal attention, so there is each layer giving only in the one color. This is all in the orange color, right? It's a bit lighter there. And then here you see that, okay, there is a particular color from blue, there's a particular color in orange and green and so on. So each of them are contributing heavily to predict the next word, and they all are likely to predict it. Okay, so now the prediction strength has increased. Now I can simply go back to the same concept and then try to use it in the case of images. So how can I use it in the images? So if I have a big block of face, right? So I assume that this part is missing. Now, given that I have the patches of all this particular image, and I see the context, there is an eye, there is an eye here, there is a mouth here, and the missing part should be, it cannot be something else, right? If you look at the rich training data, then this should be a mouth. Sorry, nose. Okay. Okay, let's take a quick demo about this next part. I hope it works. Any questions so far? I just took this one. This is a publicly available collab, and what I wanted to show was this particular part. Maybe I should just so here you can configure. So here I can say give me layer 1 and then give me the combination of input and output, and for the same example you can see how they are all changing, right? So if these are the words given on the other side, these are the words given, so what would be the occurrence for the next word? This one, this one, this one. You see this? It's a dynamic demo that is available. You can play around with that later on. And then now it's very crude, right? So now if I increase the number of layers, let's say I go to the number of layers as 5, and then I say map it from input to the output. Now you see this is the input part, and then you also see how the attention is spread across different possible words. The highest attention after D is spread for multiple things, and so on. And then if you go to a particular word here, animal, so then it says that, okay, the animal is most likely to occur with those words which are on this side, which is dust, hair, bird, and so on. I'll share this link with you. It's also in the slide, so you can play with that later on. And then I was also looking a bit around, and then I came across a very impressive demonstration. So you remember yesterday there was when Mahipal was talking, he was talking about temperature scaling and so on, how to prompt engineer, and the prompt engineering is based on everything that is running behind the transformers, right? So now here you can see some live demonstration. So I can set this one to, let's say, the temperature here. I don't know if I can actually see that there. Yeah, the temperature is set to 0.7. Maybe I just do it this way. Okay, maybe it did not take that one. Okay, now I see that. Let's try with this one. So here, so there is an example, right? So the example that I given a couple of sentences, and in the sentences that you're seeing, you can see how the attention spans changes. So let's take data visualization empowers the users to, and then what could be the next potential sentence. So here, if you see, I can put the temperature to 0, or 0.2 is the lowest one. And then I could also put the sampling to very low. Then I can now see it goes from here, and then there are a number of visualization what is happening inside the particular feature, and you see how the different aspects are getting activated. And here it's saying what is the value of the dot product, what is the scaling mask, what is the dropout, and so on. And here you see that the formula is still there, right? That was the formula we derived. Softmax of q times k transfers divided by the length of the vector. And then there is a plus m part, which is nothing but the masking part. So masking part is nothing but, occasionally we want to say that, okay, I don't really care about all the things that are getting here. I only care about certain part, and then the other things can be, it's nothing but a simple binary kind of mask, right? I'm making it very, very simple, but it's a mask, yeah. And then if you follow the same path here, now you can see at the output level, you can see how the attention is calculated. And then you can see that from this one, it shows to the, it ends up with the output that is shown here, and what is the likelihood of that next word, right? So now let's make it a bit more sophisticated, or let's see, let's go a bit further. So it says the next word is visualize. The most likely word is visualize. But it also says that if that is a given sentence, if the sentence is that data visualization empowers users to visualize the highest one with 100% probability, the score. And then it also says that there is also likelihood that it can be create, which is here. It can be see, it can be make, it can be easily, and so on, with very less probability. Right? Now this is a characteristic that has been implemented. Now let's go a bit further. Let's improve the scaling factor now, temperature factor, and then I'm going to generate it again. Okay. Now what does it say? If I'm putting the temperature factor up there, then it suddenly says that the most likely word after this particular sentence is and. Right? Now I can also see the impact of the top sampling, right? So remember we spoke about this distribution modeling, which means that we are not talking about one point, but we are talking a neighborhood of the points. If we are talking about a neighborhood of points, I can also say that pick top k and you see here dynamically is changing. The numbers are varying. So with this particular value, you see the numbers changing on the right side. Yes, no, are you able to see it or not? You are seeing the varying scores, right? Okay, good. Then I could also change this one here. Now you see that at this particular point of time, it says it's A with 2.9% probability, which is very, very low probability, right? Probably this means that we are going to discard this recommendation. All right, so I'm going to put both of these for your references, and then you can play around a bit with that. I will not get into the implementation part because the implementation part is, as Satyendra was talking in the morning, it's quite easy. You can go to the Hugging Face and then download some of the models and then start playing with them. Okay. Yeah, do you want me to go into the details of masking and positional encoding and so on? That is all math part. If you want to, we can do that, or we could say that you want to go back and then look at them and then come back and discuss.
You have 20 minutes. Oh, you have almost you have 1 hour.
Which is reserved for the next part, for the introduction to the phase part. So the question is, do you want to go deeper into the math of this one, or we say, okay, we understand the concepts of attention mechanism, and then we look into the next part of the lecture.
We can go with the math. Like the
The-
formulations.
The formulas.
Yeah.
Yeah. So formulas. How many of you are up for formulas? Raise of hands. 1, 2, 3, 4, 5. Okay, at least a couple of you. Okay, so then I'll not bore the rest of you with too much of details. At least I'll try to keep it compact, and then we can move on to the next lecture. Okay. Okay, before I go to that part, so I just want to also take this opportunity to introduce you to this vision transformers, which is nothing but the same transformer models adapted for the vision. So what happens in this case? So we start all the way with the images here. So now imagine each of this block is nothing but a word, right? It's a word, right? So you have a sentence. In our case, the sentence is nothing but the whole image. So what I do from the whole image, whole sentence, I'm going to chunk it into the different words, and this is the chunking part. So I'm going to do 16 by 16 or 14 by 14, 32 by 32, whatever it is that you prefer. And for each of these independent blocks, I'm going to extract the MLP, the embeddings, right? And then I first extract the flattened patches, and then I pass it through the transformer encoder. And at this point of time, I'm getting the tokens that I was expecting in the previous case, and that's going to give me the class, right? So the whole idea here turns down to converting this sentence into words, which is nothing but the blocking. And then from each of the words, if I have them, then all I need to do is to follow the standard pipeline, right? And at this point of time, you also have something called as position embedding, right? So because one.
We need to say that when we are doing this linear prediction of flattened patches, so you are first, suppose you have taken 12 by 12. So first 12 by 12 you will be placing one after another, then next 12 by 12 will be
Exactly.
Exactly.
So
that is
I mean,
the only thing which we are doing there.
so here you are seeing that each of them goes to that, right? So each of them are uniquely processed. So which means I could also do parallel processing. If I know that there are 8 blocks, I could extract the features from 8 of them at the same time. And then I have this 1, 2, 3, 4, 5, 6, 7, 8, 9 for all of those blocks, 9 blocks. And then I'm also encoding position. Because in the case of the images, as in the case of sentences, the place where it appears becomes very important, right? So I can't have this one here. I need to say that this appears as the first block or the 0th block, and then that's what it's coming to, right? So we are trying to keep the semantic meaning again. So now maybe you can relate to the idea that how we are capturing the context in images as well. And that's why we often tend to say that the VITs are very good at capturing the global context rather than just local receptive fields. That's mainly because of positional encoding and also because of the way each of the chunk is processed. Okay, so now just sort of curiosity, what are we doing in convolution neural networks? We are passing the whole image, right? This is not chunk; it's passed as it is, and then we let the network to learn the filters. We let the network to understand the receptive nature, local receptive fields. But in this case, we are not doing that. Okay, good. Now, if you put everything in one figure, so this is how your VIT model would look like. So this is the case for the classification. So where we are saying that we have an image from left side, we block it, chunk it into different blocks, and then we extract the embeddings here, the patch-based embeddings for each of them, and then linear projection. So we are going to get some embeddings, and then we do the position encoding. And once we have the position encoding, then we send it to the transformer, MLP, and then now we are able to get what kind of object it is. Is it a bird, frog, or so on? Okay, so this is what I was trying to cover today. But then we have a dedicated lecture on attack detection tomorrow, or maybe tomorrow, yeah. But then I just wanted to show you some practical application of this. Okay, I'll not give you the motivation and all for the time being. What I wanted to show you was something very, very simple. As I already told, that CNNs versus DETs, they have this local receptive fields based working, while DITs are DIT is another variant of transformer, which is called data efficient transformers, data efficient image transformers, which are dedicated for image processing. And they are, one thing, it's efficient, and they are also scalable. Why do I say that? If you look at the parameters, yesterday I had a question. There was a question about the computational complexity, right? So here you can see that irrespective of the number of images used for training, the accuracy is quite high for the DIT. So in the bottom part, I should not touch it. So here on the top, you can see that if you have so many images, then your accuracies will be so high, and the more number of images you have better accuracy, right? So the computational complexity is given in this paper if you go back and look at it. One variant of this particular DEIT is also based on something called as distillation, which I'll not talk about, but I'll just briefly tell what it is. It means that you have a bigger network which trains the smaller network, right? It's like a teacher and a student. So the teacher keeps on updating, and then it distills the knowledge. The student, whoever is sitting in the class, they typically distill the wide, or let's say the wide amount of knowledge that is being given, and then they take notes, right? The most critical things become as notes. So it's a very simple a very similar mechanism that we use in this DEITs, which is again a variant of transformer. And in this case, you can see that the parameter size are quite okay for an image size of 224 by 224. It's really not taking so much of space. It's not really taking so much of the computational resources. And then I'm going to give you a simple example of how to detect this, how to use it in different contexts. One of the contexts that you can use is, for instance, a classification, right? So a classification could be classifying images of just images for COVID versus not COVID. Let's say categories of different kind of cats versus dogs, right? So it's all typical binary classes. You could also have multi-classes. So in this case, we just wanted to find out the regular fingerprints, which are on the top row, versus the fingerprint that were fake. So which means it was either printed or it was created using the gummy finger. Okay, so the idea is very simple. It's a two-class classification problem. So we just took, I'll not get into all of these things, but I'll just show you something here. This might be interesting. So in the case of CNN, one of the network which is efficient at here, you see that it's capturing the images. It's telling that, okay, these are real images on the top layer, and these are fake images, right? But the interesting part here is that if you notice the attention, the network is focusing on the edges here, right? So which in theory would mean that if you're trying to classify two images, which is just image, one for COVID and the other one normal just image, and if you're looking at the edges, you're going to miss out on the diagnosis, right? So the CNNs often tend to have this problem because of the local receptive nature, while in the case of the retrained models, so they somehow adapt it, right? So the attention is now brought back from the edges to the central part. But still, if you look at this one, you can still see that the attention is spread at this particular area, which is also the background. And now in the case of the chest X-ray, it would still be something other than the chest itself, right? Which is unintended for us. And the advantage in the case of, let's go skip all this thing. In the case of the transformer based architecture, now you can see that this one, the attention is much more better as compared to the previous one. It's not solving the problem fully, but it's better, right? So at least the attention that has to be given to the central areas of the image is what it is focusing here. See this? So where the edges were destroyed due to the fake nature of the fingerprint, it has been identified in the case of vision transformers. Okay, so, and this is again mainly due to the fact that we are introducing attention, right? So if you had not introduced the attention in this case, we probably would be ending up with something similar to the top layers here. Here's an idea. Okay. I know it's a very big topic by itself. We are trying to compress everything into short sessions, which means that we have to omit a lot of details. We also have to avoid some of the complex math. So that's what we are trying to do. But I hope that this has motivated you to look into the transformers. Do we have a break or?
Yes, we should take. So we'll continue at 3:20, right? We can go for tea.
What is the time now?